Hello guys, we are back to continue free falling part 2 equations and graphs. I told you free falling is a kind of motion under the gravitational pull. We take y-axis instead of x-axis to explain the position of the object. You know that gravity is very smart and gives the same acceleration to all objects. So regardless of the mass, always the acceleration will be g to the negative direction of y. So always g is regarded as a negative value. G is almost, 9.8 meters per second square. Okay, when a quantity in general, even velocity or delta y, whatever, is measured to the positive direction of y upward, it's going to be positive, and when it's measured downward, it's going to be negative based on our convention. So let's start with the first equation, velocity time. You know that in constant acceleration, velocity is written as v equals at plus v naught. V naught is the initial velocity and a is acceleration. But here the acceleration is substituted for negative g. Acceleration in free falling cannot be anything except negative g. Initial velocity could be positive, could be negative, depending on the case. For example, suppose that one possible case is when the object is thrown upward, like that. From the ground, you may throw the object to the positive direction of y, like that. So initial velocity is a positive value. So the VT graph will be a descending line starting from positive vertical intercept. As you see, initial velocity is positive here. Here indicates the peak point. The peak point is when the object gets the maximum height and then it stops, v equals 0, and then it goes back. Like that. It's here exactly the peak point. The velocity is 0. So in this region of the VT graph, the velocity is positive rather than initial velocity, which is positive. Also, the velocity is positive until the peak point. After the peak point, the velocity will be negative because the object goes down. So here the velocity is negative. The other case is when you release an object from a certain height. Suppose that here is a cliff and then you release the object from here. The initial velocity is 0. So it's a descending line, but with no vertical intercept. The last case could be when you threw the object to the negative direction of y, downward. So you threw the object to the negative direction. Let's say the initial velocity is, 20 meters per second. So here I use the same graph, I use the same structure for VT graph, but starting from negative y-intercept. It's very important. Okay, all the lines are parallel to each other. You know that because the acceleration is always negative g, and so in VT graph, in free falling, cannot have any crossing point with the other VT graphs. So they are always parallel. It's very important. Okay, let's continue with the next equation, average velocity. You know that average velocity, like any other type of constant acceleration motion, is the initial velocity plus the final velocity divided by 2. So, for example, suppose that the motion starts from positive initial velocity like that, 40 meters per second. The descending line is like this, and then I take the final velocity to be negative 10. How should I find the average velocity? It's very easy. I just add them up and then divide them by 2. It's very important to exert the negative sign for the final velocity. Here, when any of the velocities, initial or final, are negative, you should put negative sign. It's very important. Anyway, when you add them up, you will get 30, and then it's divided by 2. So the average velocity in this case is 15 meters per second. A question, can we have negative average velocity in this case? Yes, normally in this type of motion, in free falling, even the average velocity could be negative, like this. Look at this case. Suppose that you threw the object downward, like that. The initial velocity is, let's say it's negative 10, and then the final velocity when it's about to strike the ground is negative 40 meters per second. Yeah, why not? Here, the average velocity could be negative 40, the last, plus negative 10 divided by 2. So it's negative 50 divided by 2, so it's negative 25 meters per second. Yes, it can be negative even. So don't forget, you should always take care about negative signs if there exists any negative sign in your problem. The next equation is position time. You remember in constant acceleration motion, delta x was a half of at squared plus v naught t. Here I substitute delta x for delta y and acceleration for negative g. That's all. It's not very complicated. You may be interested in writing that equation in extended format. Let's say delta y equals y minus y naught. Y is the final and y naught is the initial position. So here I can write y minus y naught equals negative a half of gt squared plus v naught t. And if I take negative y naught to the right side, the equation will be like that. It's an extended format. Y naught is initial position, y is the final position. Okay, you may remember our stroboscopic imaging. Stroboscopic imaging is a kind of time-lapse imaging or periodic imaging in which I take a certain delta t and then I take some consecutive pictures. You see the pictures are getting closer to each other when the object goes up. The reason is that the more the altitude, the less the speed. This is why the pictures are getting closer to each other in higher altitude. More than that, the YT graph must be a parabola always because it's a second order polynomial, but as the acceleration is free falling is always negative, it's a concave down graph. Concave down because acceleration is negative. It's very important. It can't never be like that because acceleration cannot be positive in free falling. Okay, here is the peak point. Pay attention to this peak point. It's very important because in peak point the tangent line is horizontal and then the velocity for a moment will be 0. For any other lower altitude, we expect a couple of points with the same speeds and opposite velocities. For example, here if the velocity is 30 meters per second, in return the velocity will be negative 30 meters per second. But the speeds are the same. It's symmetrical. Finally, I remind you again that average velocity could be delta y over t. So delta y could be v bar times t. And you remember v bar was v plus v naught divided by 2. So another format for position time equation is delta y equals v plus v naught divided by 2 times t. Let's consider some more possible cases. Let's release an object from a certain height. Release means that the initial velocity is 0. So the YT graph will be a parabola starting from the maximum. So here the initial slope will be 0 because the initial velocity indicates initial slope of the tangent line. It's 0. It's very important. The other case is something like this. You can throw the object upward and then it goes down. Here basically it starts from a positive y naught because the y naught is positive above the ground, and then the final point, the destination, is on the ground. The other could be like that. You start from the ground and but the destination is above the ground. So the YT graph starts from 0, but the destination will be here. The last equation will be time independent. You remember in constant acceleration motion, v square minus v naught square is 2a delta x. Here acceleration is substituted for negative g and delta x for delta y. That's all. But pay attention, here we have an elegant point. Delta y has a free sign. It could be positive, could be negative. For example, let's say v is something we are going to find. V naught is 10 and delta y is negative 3. What should I do with that? Oh, here I should put the negative sign in the equation. So I will write v square minus 10 squared is equal to negative 2 times 9.8 for g times negative 3. It's very important. Delta y must keep its negative sign. How to determine delta y? I again remind you. Suppose that the object starts from a point above the ground. Let's say it's from top of a cliff and then it goes down. So normally delta y is a vector drawn downward, so it will be negative. The other case is like this. The object starts from top of a cliff and then comes down. When the destination is on the ground, delta y is a negative value. And when the object starts from the ground and ends at a point above the ground, normally the delta y is expected to be a positive value. And the last case is when the object starts from a point and ends at the same point. So there is no delta y here. The right side of the equation will be 0. Let's check our understanding. As you see, here is a ground to ground case. The object starts from the ground and then goes up, then goes back again to the ground. So the destination is exactly the same point it has already started from. Here is the peak point. It's very important. It's the peak point in which the velocity is 0, and also the velocity here is 0. It's the peak point. When the object goes up, the velocity is positive, and also the initial velocity is positive, as you see. When it goes back, the velocity is negative. Yt must be negative a half of gt squared plus v naught t. There is no y naught because the object starts from the ground. There is no initial height. And finally, the velocity will be negative gt plus v naught. V naught is positive. The other case is when the object is thrown upward from top of a cliff. So I have y naught. It's not 0. The yt graph will be a parabola again, starting from h here. And this is again the peak point. Nothing very special. How to write the yt? It's very easy. Yt is negative a half of gt squared plus v naught t plus h. H here is the y naught. And velocity negative gt plus v naught. The next case is when you release the object. There is no initial velocity but initial height. So y starts from h. It's very important here, but no initial velocity. So here the graph has a maximum point and the tangent line is horizontal. So the initial velocity will be 0. Also here you see that the vt graph starts from 0. Always the velocity will be negative, and the yt is written as negative a half of gt squared plus h. V naught here is 0, so we don't write it anymore. And v is negative gt. Again, v naught eliminated. Finally, I may have the case in which I threw the object downward, but from top of a cliff. I have y naught to be h, so the graph starts from y naught, h here, but the velocity is negative, initial velocity is negative, so at the beginning the yt graph will have a negative slope. As if you draw the tangent line, it will have negative slope. V naught is negative. And also you see that vt graph starts from negative vertical intercept. Finally, y is equal to negative a half of gt squared plus, negative v naught t plus h. Negative v naught because we threw the object downward. Finally, v is negative gt, negative v naught t. Again, negative sign is seen here. Thank you again for being with me. Review the lessons. I will see you in the next video with problem solving.